What is frequency response in signal amplification? Imagine you're listening to your favorite song and notice some parts sound clearer while others seem muffled. That's a bit like what happens inside an amplifier when it processes different signals. Today, we're going to uncover what frequency response really means in signal amplification and how it impacts the way signals are processed and controlled. Frequency response describes how an amplifier reacts to different input signal frequencies. It shows how much the output signal's amplitude and phase change when the input varies across a range of frequencies. Think of it as a map that tells us which frequencies an amplifier can boost well and which ones it struggles with. This is important because real amplifiers don't boost all signals equally. Some frequencies get amplified more than others, which can distort the original sound or signal. In electrical engineering, we analyze this by measuring the gain, which is how much the signal is increased, and the phase shift, which is how much the signal's timing is altered. These measurements are taken across a spectrum of frequencies. Usually an amplifier has a certain range called the bandwidth where it maintains a nearly constant gain. This is called the midband region. Outside this range, at very low or very high frequencies, the gain drops off. The points where the gain falls to half of its maximum value are called the lower and upper cutoff frequencies. These define the limits of the amplifier's effective bandwidth. Mathematically, the frequency response is often shown as a transfer function, which is a complex number that relates the input to the output in the frequency domain. The magnitude part of this function shows how much the signal is amplified or attenuated at each frequency. The phase part indicates how much the signal is shifted in time or phase. Understanding the frequency response is key when designing amplifiers for specific tasks. For example, audio amplifiers need to work well from 20 Hz to 20,000 Hz, which covers the range of human hearing. Radio frequency amplifiers focus on much higher frequencies. Components like transistors, capacitors, and resistors influence the shape of the frequency response curve. Capacitors and resistors in the circuit determine how the gain varies with frequency, shaping the overall response. In practical applications, knowing the frequency response helps engineers avoid unwanted distortions. If an amplifier boosts some frequencies more than others, the sound or signal can become uneven or distorted. This is especially important in audio systems, communication devices, and control systems where signal clarity and stability are essential. So, in simple terms, frequency response tells us how well an amplifier can handle different signals across a range of frequencies. It shows us the limits of its effectiveness and guides us in designing systems that deliver clear, accurate signals without unwanted changes.